This video is for Assignment 3, Group 9, AI for Engineers. We are doing the motor action prediction from EEG data task, which involves using EEG data to classify various motor skills as performed by some participants.
For our literature review, our team investigated established academic practices to effectively pre-process EEG data for motor imagery classification tasks. Through our research, we found that EEG signals associated with motor actions predominantly reside within specific frequency bands, notably the mu rhythm around 8 to 12 Hz and the beta rhythm around 13 to 30 Hz. Most academic papers recommended applying a bandpass between the ranges of 8 and 30 Hz. Filtering this range enhances the relevant signals related to motor imagery while reducing noise and artifacts from other frequencies, particularly those below 8 Hz with slow cortical potentials and artifacts, and above 30 Hz where signals typically contain high frequency noise and muscular artifacts. We further explored other neural network architectures commonly employed for EEG classification. Our findings revealed that convolutional neural networks, CNNs, recurrent neural networks, RNNs, and transformer models are prevalent due to their capability to handle spatial and spectral EEG characteristics effectively. CNNs particularly stood out to us for their ability to capture spatial frequency patterns crucial for motor imagery EEG tasks.
At the moment, we've got a baseline model which has between 30 and 35% accuracy for training and validation sets, and this baseline model is a multi-layer perceptron with 2 deep dense layers. As for pre-processing, we've one-hot encoded the labels.
So for the implementation, current progress, and future plan, regarding our implementation current progress, we've systematically approached the task using the baseline feed-forward neural network model and incremental introduced the various refinements to improve its accuracy. Initially, the baseline model without specific pre-processing technique achieved approximately 32.51% testing accuracy, which serves as our starting benchmark. We implement improvements individually to clearly understand the impact. The first thing we did is bandpass filtering, which range between 8 to 30 Hz. By focusing on only the relevant EEG frequency, which range from 8 to 30 Hz, mentioned by Tim, the model accuracy significantly improved to 41.96%, confirming the importance of targeting the mu and beta rim as advised by the literature. And secondly, we implemented dropout regularizations by adding dropout layers to each hidden layers to combat overfitting dramatically, which improved the test accuracy up to 61.72%. Notably, this approach achieved a minimum difference between the training accuracy, which is 62.58%, and testing accuracy, and that highlighting the effectiveness of the generalization. And thirdly, we implement the class normalization to ensure an equal number of samples per class. Surprisingly, it did not yield better results than the baseline, obtaining only around 34.03% testing accuracy, even with longer approach. This indicates that class imbalance might not be as influential as initially hypothesized. The current encounter issue and reflection we are facing, there's a key takeaway was that the dropout regulation and targeted frequency filtering provides substantially and reliable improvements And conversely, class normalization did not quite meet the expectation, and possibly due to already reasonable balance the inherent complexity in differentiating EEG signals among classes. And our future work will involve more intensive hyperparameter tuning, such as adjust the dropout rates, number of neurons, learning rates, schedule, or to optimize the model further. Additionally, we plan to implement and compare advanced neural network architecture, such as transformers or convolutional neural network, which have shown the promising result in recent EEG studies due to their ability to capture the complex long-range dependency in the EEG signal, which is lost in the fast Fourier transform and could not be captured by the LMLP. Our goal is to develop the well-optimized model by our final submission, or potentially 2 models, so we can compare the pros and cons, supported by comprehensive comparative results in robotic analysis. Thank you for your attention. We're happy to address any questions or receive any feedbacks on our approach. You guys can reach out to us in email or via the Canvas assignment comments. Thank you again for your attention, and wish you have a nice day.